All right, so the last transformation we're going to look at is probably the easiest one to identify, and that's the vertical shift. Now, the best way to explain, I believe, the vertical shift of the graph is the movement of the midline. When we talked about amplitude, okay, I think I started calling it the line of equilibrium or whatever you want to call this. The midline, the graph is going to oscillate over and above that, and the distance between the max and min is going to be the same from that midline, right? So in essence, the quote unquote midline, the location of the midline of any wave is the midpoint between the max and the min. Okay, average the two. Just as an example here, and we'll get back to that other slide in a second, but what is the average of 1 and -1, right? The minimum is at -1, the maximum is at 1. If we average these, we get 0/2, which is 0. And that gives us, so it's really y equals 0 as the midline of the wave, okay? The vertical shift of a graph changes the midline of the wave, right? So vertical shifts are what we call rigid transformations. They don't stretch, they don't shrink, they just move the whole thing as one piece, okay? So when we are shifting a graph, right, we've talked about transformations how many times now? Okay, we've built this all the way to this point. If you've watched these in sequence, we have the amplitude as the coefficient of sine. Whoops, got a little ahead of myself there. Okay, and then quote unquote inside the function, we have the phase shift. We have B, which alters the length of the period. We have C, which horizontally shifts the graph. Okay, how do we do vertical shifting? How did we shift graphs vertically in the past? Shifting is always an addition or subtraction operation, and it occurs outside the function. Now, pretty typically where we see that is actually in front here, okay, with this D variable, and then this will either be a positive or negative symbol here. Now you can put that at the end as well, okay? We've referred to this in the past as the floating constant. It's not attached to any other term in the expression. So the floating constant determines the vertical shift of the graph, right? It might be put in the back and be minus D. It might be put in front and be positive D, okay? But that's what's going to identify what moves the graph up or down. I'm going to stay here just for a second because we haven't necessarily talked about reflections that much, and I'll do that now. The reflection is a type of transformation that we've discussed before, but it's not something that gets explicitly asked about sine functions. Okay, so we've been pretty much dealing with the new terminology that we deal with sinusoidal waves, right? Amplitude, period length, phase shift. Reflection is a transformation that we've discussed before. Okay, the reflection of a graph is determined by multiplying by a negative, right, or making the opposite of the coefficient of the function. So what we'll say about the reflection is this: amplitude is always positive. This number, when you are asked what is the amplitude of a sine wave, it is the absolute value of whatever this number is. But if this value is a negative, the entire graph flips over. So instead of going from intercept to max to intercept to min to intercept, the graph would come down and then up and then over. Okay, so it flips the whole thing over when the quote unquote amplitude, or when the coefficient of sine is negative, the whole graph flips over. So that pattern of critical points is flipped over as well. Intercept, min, intercept, max, intercept. Okay, so even though I don't believe you'll ever technically be asked for the reflection, you need to understand that changing the coefficient here to a negative will flip the graph over. Let's take a look at some of these transformations. I'm going to bring these back just because it'll be easier for us to look at. Okay, so here's our basic sine wave. Okay, we talked about here's A, the amplitude, right? Here's the vertical stretching. Notice that the anchoring points, the intercepts don't change when we change the amplitude. Those stay, right? We're just stretching it. And if we bring this, watch very closely, as we get to the negatives, that's where it flips over. Okay, so when A is negative, that's when we see the reflection. Okay, this value of D, we're going to see this whole graph slide up and down. Okay, and again, because it's outside the function, we follow conventional logic where if we're adding, it goes up. If we're subtracting, it goes down. All right. Now let's zoom out here for a second just to reiterate something else, and let's bring this back to, let's say 2, and let's shift this up 4 units. Okay, because we're going to write one more thing back on that slide. Come on. All right, got it. Okay, talked about how the value of D is the average of the max and the min. Okay, the max here is 6, the min is 2. The average of 6 and 2, 6 plus 2 is 8. 8 divided by 2 is 4. So if we type y equals 4 here, we see that midline, okay, where that cuts right through the graph. So as a formula, right, we've had formulas for almost all of these. As a formula, we could say here that D, which is the variable that dictates the vertical shift, D is equal to the average of the max and the min. So we can add the max and the min and divide by 2 to get the value of D, okay? That's going to be important when we're looking at tables, when we're trying to identify the function from the graph, okay? All of that's going to be important once we start doing that. All right.